Yeah, thank you. So today I'm kind of like a pinch hitter, but today I will talk about the spin-orbit-induced spin polarization in semiconductor nanostructures. So my name is Makoto Kohda from Tohoku University, and my message is we can generate the spin polarized current without the external magnetic field and also the magnetic materials. And why we can do it is because we use such a narrow constriction in semiconductors with the strong spin-orbit interaction, and that makes the Sendai type spin separation here, and we can generate the spin polarized current at zero magnetic field. So here is my content. This is my context of this talk. So first I will explain the fundamental technologies for the Spintronics, and afterwards I will present the spin-dependent force is really key for the spin generation and the spin detection. And to realize this, we employ the quantum point contact structure, and I will explain the detail of the result. Okay, so the fundamental technologies for Spintronics are electrical spin generation, spin manipulation, and spin detection. And we would like to realize these three technologies without external magnetic field and also the magnetic materials, because when we can do it, we can seamlessly integrate these three technologies into the single semiconductor device without the ferromagnets or the external magnetic field. So to realize this, we focus on the spin-orbit interaction, because the spin-orbit interaction induces the effective magnetic field. So that means when the electron is moving to the one direction, the electron spin feels the effective magnetic field perpendicular to the spin direction. So this spin starts to rotate around this effective magnetic field without external magnetic field and also the magnetic materials. So in order to, by using this advantage, already the electrical control of the spin precession has been demonstrated by using this spin-orbit interaction in such a spin interference device, and also recently with the spin Hall effect transistor structures. However, the electrical spin generation and the spin detection by using the spin-orbit interaction are still challenging problem, especially in the semiconductor 2D structures. And one stimulating experiment has been, for the spin generation and the spin detection has been done in 1922 by German scientists Otto Stern and Walter Gerlacher. And what they have done is like this. So they prepared the melting silvers in furnace and also the different shapes of the magnet facing each other. So this induces the non-uniform magnetic field in this region, and the evaporated silver particles are going through this region. Then after that, the silver particle with the spin up and the spin down spin up and spin down momentums are spatially separated and deposited like this. So why this happened is, first, so they use the ferromagnets. So that means the Dema energy here. And this Dema energy is described by the 2 times mu b ms by. And the mu b is the Bohr magneton, and the ms is the spin angular momentum, and the by is the strength of the external magnetic field along the y direction. And if this Dema energy has spatially dependent like this, so it becomes the force. So that means in this experiment, so they use the different shapes of the magnet. So that means the external magnetic field in this region is not uniform. So there is an external magnetic field gradient along the y direction, and this takes this term. So external magnetic field gradient, and also the spin angular momentum of these silver particles are either +1/2 or -1/2. So that means the sign is different. So this force acts to the opposite direction to the spin up and the spin down. So that's why we can separate the spin up and the spin down angular momentum by this experiment. So from this experiment, such a spin-dependent force is a really key for the spin generation or spin detection. So we want to use it in the semiconductors. So how we can achieve this? So simple idea to use this spin-dependent force is to shrink entire structure in a micron-sized device. So for example, so here is one example. So this black region corresponds to the semiconductor two-leg structure. So here is a quasi one-dimensional wire structure here. And these two are ferromagnets based on the permalloy and the cobalt. And since the saturation magnetization of these two materials are different, so we can generate the story field gradient along this direction, y direction. So this is a calculated story field in this system along the y direction and also the x direction. And this x direction is along the y direction. So in this system, we can generate the story field on the order of the 0.4 Tesla within the submicron region. So, but however, when we use such a ferromagnetic thin film, the story field is not only in plane direction, but also there is some out of plane component. And this perpendicular story field component modulates the electron orbital motion by Lorentz force. And this Lorentz force is much stronger than the spin-dependent force. So sometimes it is difficult to observe such a spin separation by using these micromagnet structures. So to overcome this obstacle, we use the spin-orbit interaction. So I will explain a detail of the spin-orbit interaction here. So this is a schematic dispersion relationship for the conduction electron. So this vertical axis is the electron energy, and the lateral axis is the electron, the wave number. And if the spin-orbit interaction is really small, then the spin up and the spin down subbands degenerate each other like this. However, when the spin-orbit interaction becomes strong, then this spin up and the spin down subbands are split into the k vector direction, and there is some finite spin splitting energy called the ESOI. And this spin splitting energy is simply described by the parameter alpha and also the Fermi wave number here. And for electron spins, so this energy is spin splitting. So we can describe this spin splitting energy by using the effective magnetic field, which is the same description of the Zeeman energy term. And this effective magnetic field is proportional to the electron momentum and also the internal electric field. So this is happy for us because we can generate the effective magnetic field without external magnetic field and also the magnetic materials. But however, for the spin separation, this is not enough because we need a field gradient, so not field itself. So for the spin separation by using the effective magnetic field, we need an effective magnetic field gradient. So how we can make it in the semiconductors? And to realize this, we need more focus on this formula. And when we so here, so this is a energy potential band diagram of the semiconductor two-leg structure. And the electron is sitting down in the bottom of the potential. And basically, the quantum error is based on the indium gallium arsenide material. And this material is sandwiched by the barrier materials. For example, like indium phosphide and also the indium aluminum arsenide. And since the electron is confined in the XY plane, and also there is a potential gradient here. And this potential gradient induces the internal electric field. So when the electron is moving to the y direction, then the internal electric field is a z direction. So we can generate this effective magnetic field along the x direction. And this effective magnetic field is proportional to the internal electric field. So when we make such a symmetric quantum well structure, that means there's no potential gradient. So in that case, there's no internal electric field. So the effective magnetic field becomes really small. However, when we make such a asymmetric quantum well, then we can generate the internal electric field. So we have a large effective magnetic field strength in this structure. So by changing such an internal electric field, we can modulate the effective magnetic field inside of the semiconductor structures. So in order to use this idea in a real device, we employ the quantum point contact structure. So generally, the quantum point contact structure is based on the semiconductor two-leg structure. And also here is two metal gates on top of on the surface of the semiconductor two-leg. And when we apply the negative Keio bias voltage here, then electrons start to deplete in this region, and we can make pure one-dimensional channel here. And when this lateral confinement is strong enough, then we can generate such a quantized conductance channel. For example, this is a single channel here, and this is a two channel in between here. And since this lateral confinement is really strong in this area, the potential structure is spatially modulated like this. And the x direction is along the channel direction, and the y direction is a perpendicular channel. And when we focus on these two different points in this structure, so one is just above this conduction electron channel, and the other point is the start to deplete because of the lateral gate bias voltage. And when we compare the quantum well structure, so first, when we look at this red point, and since the electron is here, so that means that we have a large electron wave function in the quantum well, and potential gradient is also large like this. However, when we look at this blue point, the electrons start to deplete because of the side gate, so the electron wave function becomes small, and also corresponding the energy potential gradient also becomes small. So that means we can, and also since the effective magnetic field is proportional to the internal electric field, so we can modulate the effective magnetic field strength by using this potential gradient. So that means such a lateral confinement structure induces the spatial modulation of the effective magnetic field, which takes this term. So that's why we can induce the spin-dependent force by using the effective magnetic field in the quantum point contact structure. So we prepared two kinds of the sample. And before that, so we fabricated such a trench type side-gated quantum point contact structure based on the indium gallium arsenide and also the indium gallium arsenide phosphide two-leg structure. So these two are side gates, and here is a source, the source side, and this side is a drain side. And when we calculate the corresponding potential landscape of this QPC, so this is a calculated result of the potential landscape. And since we etch this black region, so we have a strong potential modulation like this. And this part is the center of the channel region, and this is analogous to constriction corresponding to this point. And when we calculate the effective magnetic field along this red line, the result is like this. So at the channel center, we have an effective magnetic field on the order of the 10 Tesla, which is really strong. However, this effective magnetic field is gradually decreased and goes to 0 because of the carrier depletion. And we have such a nice effective magnetic field gradient like this. And the important point in this structure is the sign of the effective magnetic field gradient is the opposite for the left side and the right side. And this makes the interesting spin polarized mechanism in this structure, because since the sign of this term is opposite for the left side and the right side, so that means for one electron spins, the spin-dependent force is acting to the opposite direction for left side and the right side. So that means the only downspin is accumulated at the center of the channel, and the upspin is away from the center. And only this downspin at the center position can go through the QPC structure, and we can make the spin polarization. So this is what we expect in this structure. So we fabricated two different samples. The one is the little bit wider channel width for 50 nanometer sample, and the other is a 360 nanometer sample. And this is an entire device structure. So here is a side gate, two side gates, and this is a one-dimensional channel here. And also, we fabricated the top gate to control the carrier density and also the strength of the Rashba spin orbit interaction. And here is a detail of the measurement conditions and also the measurement methods here. And first, we measure the quantized conductance by controlling the side and the top gates. And here is the result. So there are two different samples, and the lateral axis is the side gate bias voltage, and the vertical axis is conductance. And first, we set the top gate bias voltage to be weak Rashba spin orbit interaction. Then we observe such a quantized plateau from 1 to 3, and also from 1 to 5. So that means we can successfully generate the pure one-dimensional channel in this structure. Then, when we change the top gate bias voltage to enhance the Rashba spin orbit interaction, then we additionally observe the quantized plateau around 0.5 to E square over H, like this. So this 0.5 plateau strongly indicates the spin polarized single channel formation at zero magnetic field, because so far we don't apply the external magnetic field. And so in order to explore this 0.5 structure and to catch the characteristic feature of the spin orbit interaction, we first calculate the wave packet dynamics in this structure. So this is our model. So we prepare such a quantum point contact structure, and we inject the wave packet into the narrowest constrictions. And around this region, we take into account the spin-dependent force induced by the effective magnetic field gradient. And this is a charge density, and this is a spin density. And this arrow position corresponds to the narrowest constriction of the QPC structure. And when we inject the wave packet, then spin up and spin down density are spatially separated like this. And only this down spin can go through the narrowest constriction in the QPC structure. And we can generate the down spin polarization. And this is what we expect in the before. And the characteristic feature of this effective magnetic field is this effective magnetic field direction is momentum dependent. So that means when the electron is moving from left to right, then effective magnetic field becomes the downwards. However, when the electron is moving to the right to left, then the effective magnetic field direction becomes the upwards, because of this one is momentum dependent. So that means we can expect the opposite spin polarization when we change the electron momentum direction. So so to calculate this, so this is what we expect based on the effective magnetic field description. And to check this, we calculate the momentum-dependent wave packet dynamics. So upper panel shows the electron is moving from the left to right. So in that case, as we see in the previous slide, we can generate the downspin polarization at the center, and we can generate the downspin polarization. However, when the electron wave packet is moving from the right to left, then we can generate the upspin polarization. So which color? This color is opposite to this. Then we can generate the upspin polarization after the wave packet go through the narrowest constriction. So this is really characteristic feature based on the effective magnetic field. And in order to catch this point in the experiment, we prepare the following setup. So as we see, depending on the electron momentum direction, we can expect the opposite spin polarization. And since we can change the source joint bias voltage direction, and then we can change the momentum direction. So that means when we apply the positive source joint bias voltage, then let's say downspin is polarized in this case. However, when we change to the negative source joint bias voltage, then we can get the upspin polarization. And there is some finite spin splitting energy like this. However, at zero magnetic field, we cannot distinguish these two states because the spin splitting energy is almost the same. However, when we apply the in-plane external magnetic field parallel to the spin direction, so what happens is when this in-plane magnetic field is parallel to the spin direction, then spin splitting energy is enhanced due to the additional Zeeman energy contribution. However, this in-plane magnetic field is the anti-parallel to the spin direction, then this spin splitting energy is reduced. So under the external magnetic field, we expect such an asymmetric spin splitting, and this is a sign of the momentum-dependent spin splitting structure. So to measure this, we employ the transconductance measurement, because transconductance measurement can approach these two spin splitting subbands. And here is a result for without external magnetic field and the application of the H Tesla magnetic field. And this is a source joint bias dependence of the transconductance with the side gate bias voltage. How we can analyze this is such a red line. This red line corresponds to the energy crossings between the source drain chemical potential and these spin splitting energy levels. So that means at zero magnetic field, this energy crossing line shows the symmetric to the positive and the negative source drain bias voltage. So that means we can get such a spin splitting structure. However, when we apply the external magnetic field, we observe such a asymmetric spin splitting structure. And in order to understand such a spin splitting structure really comes from the momentum-dependent spin splitting, so we calculate the transconductance. And I will skip the detail of the calculation method, but generally the conductance is described by the transmission probability in the QPC and also the source drain bias energies. And in the transmission probability, we take into account the momentum-dependent spin splitting and also the Zeeman splitting because we apply the external magnetic field. And we calculate the transconductance at zero magnetic field and also the H Tesla. And when we compare these two results with the experiment, such a symmetric structure and also asymmetric structure is well reproduced in the calculation. And so that's why we experimentally demonstrate the electronic spin separation or spin polarization by using the Strangler type spin separation mechanism in semiconductor nanostructures. So now we can generate the spin polarization. So the important parameters for the spin generation or spin detection, one is the spin splitting energy, because spin splitting energy determines the temperature of operations. And the second one is the electron spin polarization, because electron spin polarization also determines the spin injection efficiency and the detection efficiency. So to evaluate these two parameters, we first measure the transconductance measurement like this at different top gate bias voltage. So here is a quantized conductance at different top gate bias voltage, and that makes the with 0.5 structure and without 0.5 structure. And in this top gate bias conditions, we measure the transconductance, because transconductance can get the energy levels in the QPC structure. And here is a result. And this dark point corresponds to this plateau region. So for example, so this region is 0.5 plateau, and this region corresponds to the 1 plateau. And these red points, so these red points corresponds to the characteristic bias voltage. So which means the source drain bias voltage is so source drain bias energy is the same as the subband energy or spin splitting energy. So from this source drain bias voltage, that we can evaluate the subband energy and also the spin splitting energy. So in that case, the subband energy is around 5 millieV, and the spin splitting energy is around 4 to 6 millieV. And when we compare this spin splitting energy to the different materials, for example, gallium arsenide based the QPC structure, and in the gallium arsenide QPC structure also 0.5 structure is observed. And this is the same transconductance measurement. And this point is around 1 millieV. So that means the spin splitting energy in the indium gallium arsenide structure is much higher than the gallium arsenide QPC structure. And this large spin splitting is also reflected in the temperature variation of the 0.5 structure. So here is the result. So this is a quantized conductance at different temperatures from 0.3 Kelvin to 16 Kelvin. And this is a 0.5 plateau. And we still weakly observe the 0.5 plateau even at the 16 Kelvin, which is a relatively large temperature, the higher temperature than the gallium arsenide QPC structure. And this is because the large spin splitting in these systems. And finally, we evaluate the electron spin polarization by using the shot noise measurement. So shot noise is the kind of like a particle nature of the electrons. So that means, so shot noise signal is described by the charge Q and the time average current I. And for example, in the non-electron correlation case, which means for example, the electron emission from the vacuum tube. So in that case, there is no interaction between these electrons. So in that case, the charge equal E. However, in the case of the strong correlation case, for example, like a Cooper pair. So Cooper pair means the two electrons strongly correlating each other. So in that case, the charge Q equal to E. So this charge Q is really reflected the particle nature of the electrons. So this is a really powerful tool to investigate the electron correlation in the system. And in our case, the electron correlation is the Pauli exclusion principle because we have a spin. So that means the shot noise signal for the anti-parallel spin and the parallel spin would be different. And this exactly corresponds to the spin polarization. So that's why we can evaluate the spin polarization by using the shot noise measurement. And usually the shot noise can tell the transmission probability for spin up and spin down. So here's the result. And this orange curve corresponds to the conductance. So this plateau region corresponds to the 0.5 structure. And this is a transmission probability for downspin and upspin. And around this 0.5 region, there is a large difference between the transmission probability for the up spin and down spin. And by using this formula, we can evaluate the spin polarization. And around 0.5 structure, we obtained the 70% spin polarization without external magnetic field and also the magnetic materials. And even lower conductance, we can get the higher spin polarization, almost the 100%. Okay, so finally, I acknowledge these peoples. So in Tohoku University, the Professor Nitta supported me a lot, and also for the short noise measurement, the Professor Kobayashi and Professor Ono they support us. And in the theoretical calculation, the Professor Oe and the Professor Tokura support us a lot as well. And finally, I conclude my talk. So we present the electrical spin generation by using the spin-orbit interaction. And such a spatial modulation of the effective magnetic field is really key because it generates the spin-dependent force. And and we observed the 0.5 structure, and around this 0.5 structure, we have a large spin polarization as a magnetic field. So thank you for your attention.